Before to start the third section, I just want to say something about the last example of this morning. So, the examples of this morning. So we had the Q, which goes from C3 to C. And we look at x0, the fiber over 0, and x1 over the fiber over 1. And in fact, we can look at all fibers. And for t different from 0, we will see that x of t is the same as x1. So in fact, we have construct so a degeneration of x1 into x0. So to x0, or deformation of x0 into x1, and this is a general setting. So you always have a degeneration of spherical variety. Spherical varieties to oral spherical varieties, or to toric varieties. But remember that x0 was singular, so we don't keep the same regularity when we degenerate these varieties. So if we start with a smooth variety, we don't have in any case smooth variety when we degenerate it. Okay, so now we speak about classification of spherical homogeneous space. Okay, so the three next part will be very independent. So my next three talks will be independent from the others. So first, let me say a theorem of Hausdorff from so it will be. It is published this year, and so the theorem is the following. So we take G mod H1 and G mod H2, such that both are the same weight lattice, so the same M. So the lattice of weights on the rational function of each of the homogeneous space, and also the same variation cone. And so with colors. So the set of colors are denoted by D1 and D2, and with a bijection between the two colors, such that and for each color we have sigma 1 and sigma 2, so the map from the colors to N, and we ask that this bijection satisfied, that for all color in D1 we have sigma of D equals to donc sigma 1 of D equals to sigma 2 of iota of D. So it said that the colors are the same and even with their applications. And the image of colors are the same. And we have a second condition which says that the stabilizer in G of D, so always for all, so maybe I can put, so we have two conditions for all D in D1. So the stabilizer of D in G is equals to the stabilizer in G of iota of D. So this is one more invariant here I introduce. So if we have all this hypothesis, then G mod H1 is isomorphic to G mod H2 with G equivariant isomorphism. So it's a theorem of unicity of a spherical homogeneous space with a given combinatoric. So the weight lattice, the variation cone, and the colors satisfying the this condition. And also this condition, maybe I can give a very simple example. So if you look at flag varieties, so you look, for example, at the Grassmannians I n and Grassmannians J n. So we see that for both M is 0. For both, the variation cone will be also the same. And for both, the colors will be, so there is only one color. Here it will be D alpha I, and here it will be D alpha J. So we have a trivial bijection between both. And for wait, no, it's not. Yes. So here on the map sigma, so sigma I of D I will be 0, and sigma J of D alpha J will be 0. So we have all conditions satisfied here except this one, because the stabilizer of D alpha I in G is different from the stabilizer of D alpha J. Because here, if I is different from J. So in general. So we have different stabilizers, so we don't have isomorphism in general between the Grassmannians with I and J different. So that's why we ask this condition. So there's also examples not for flag varieties, or for spherical varieties. So here is a theorem of uniqueness, but now the question is to know is if we have M nu D sigma and stabilizers of so a set of stabilizers of D for all D in D, is there exist G mod H spherical with this there's invariance. So in general, the question is not known.
But in this theorem, does this imply that H1 and H2 are conjugate? I mean, equivalent.
Yes.
Conjugate.
Yeah.
They are really.
Yes, because G equivalent means that so Gx is mapped to G times phi x, which is a phi of Gx. So yes. So in fact, we can answer only on a very particular case. So in the general case, we can't answer. So for all spherical varieties, so it's not very difficult because we have M. So if we give us M and I, including S, such that M is a sublattice of the characters of Pi. Then we define H as the intersection of the kernel of chi with chi in M in Pi, and G mod H is all spherical. And this gives a bisection between all spherical varieties and such set. So here, so we have already seen that for if we fix this, we can define the colors. So the color are S minus I, and then the map sigma is also defined by the co-roots. And the stabilizer here is in fact defined by Pi. So correspond to Pi or to a conjugate of Pi. Okay, so in that case, we have answered the question. So there's also one case where we know the answer, so partially the answer. One case is the symmetric space, symmetric varieties. So we say that the definition. So we say that G mod H or a G mod H embedding is symmetric if there is this theta and evolution of G such that H is contained between the fixed point of theta and the normalizer in G of the fixed point of theta. This is a fixed point of G by theta. So we have already seen examples. So the example X1 of this morning. And so the second example I gave, so taking the normalizer here was also symmetric with this definition. So the involution was classified in the 20s. So classification of involution of G. So here I suppose that G is semi-simple. So the classification of involution of G was given by Cartan. So almost 100 years ago, so in the 20s, and in in 1990, Wust describe the M, nu, and the colors for all symmetric space. So symmetric G mod H. So let me try to explain very quickly how to describe this. So first we define T1, so a maximal torus, such that for all t in T1, theta of t is equals to t minus 1. So it's a maximal with this property. And then we take t, a maximal torus of G containing this T1. Okay. And yes, then fact, so theta stabilize T. So we can. So then when we from G and T we define the root system. So since theta stabilizes T, we have an action of theta on the roots. So the roots defined from G and T. So T1 is maximal with this property. So when I say so, it's a torus maximal for this property. So that theta of t is t minus 1, and in t there's some elements so that theta of t equals t. Yes, sorry. Yes, T1 is included in T. So we have an action of theta on R. So we can define R G theta as the set of alpha minus theta alpha for alpha in R. Okay. So we can. So it's also a fact. So I don't prove anything, but I just want to give the results. So there is so we can choose B such that. So when we choose B, we choose also the positive roots. So the choice of B gives the choice of the define the positive roots, and then we choose B such that for all positive roots we have theta alpha equals theta, or theta alpha is a negative root. And so there's two parts in this fact. So second fact is that for this for such a B, we have BH is open in G. So in other words, B has an open orbit in G mod H. So in particular, it proves that symmetric implies spherical. Which a priori is not given the definition of symmetric. Okay, so now there's so we can also define. So there's another fact is that R, G, theta is a root system. So it's a set of roots. So we can define S, G, theta by the set of alpha minus theta alpha with alpha in S, and this is the simple roots. So a set of simple roots of the system. Of the root system G theta. So RG theta is called the restricted root system. Okay. So now we have all to describe what we want to describe. So the theorem of Hausdorff. It says that so if we have G mod H, we have M is the characters of T1 quotiented by T1 intersect with H. We have nu is so the valuation cone is the antidominant chamber of R, G, theta dual. So I will give some picture later to explain this. The image of colors. So if I denote this set by the set of gamma 1, gamma R, then the image of the color are exactly the gamma 1 dual, so the co-roots of the gamma I. And for all gamma I, there exists one or two colors of G mod H with image gamma I dual. So I don't choose the good place to write the theorem, but maybe I wait that you.
What is one and next one?
What is T1? I don't know why we call it T1. No.
Or gamma I, there is the last sentence.
As the last sentence is one or two. One or two colors. So there is at most one color. And at least one, because it's image of colors. So here we don't describe exactly all the colors, but it will depend of the H we choose between the fixed point and the normalizer of the fixed point. So all this only depends on theta. It does not depends on really on H. So here it depends on H, but in fact I don't think it depends on H. But so the choice of H between the normalizer and the fixed point. So we will give the fact that we have one or two colors for an image. Okay, so maybe now I can. So here I consider 4 cases where So for case where the rank of the group is 2, so that's why we have picture in dimension 2. So the first one is for G equals SL3. So we have the hexagon here, which corresponds to the root system of G of SL3. And then, if we consider theta, so if we consider H to be SO3, then theta will act on the roots by minus identity. So it sends alpha to minus alpha. And then the restricted root system will be the system which big circles. So 2 alpha 1 and so 2 alpha 2 are the simple roots of the restricted root system. And then the variation cone is the antidominant chamber. It means so it's the opposite of the dominant chamber are defined on Monday. And what to say more? And yes, so the co-roots gamma 1 dual and gamma 2 dual are in gray, so gray circle. And so here we have so M of rank 2 and the variation cone and 2 colors, 2 images of colors. But maybe we can have 2, 3 or 4 colors. So the second example is SL3, but we mod out by GL2 instead of SO3. And in that case, so I did a mistake. So the theta is just a reflection. So the line reflection by this line, and not this one. And so for the restricted root system is of rank 1, and so G mod H will be also of rank 1, and so we have the variation cone, which is the half line here, and we have one color here, gamma 1 dual. And then we have also other examples. So here the square is the root system of SO5. So in both cases, and in the first case, theta acts by minus the identity on the root system. And then the restricted root system corresponds to 2 alpha 2, 2 alpha 1, and all roots generated by them. And you have also the variation cone, which is the antidominant weight, antidominant chamber, and we have two images of colors, gamma 1 dual and gamma 2 dual. And in the second case, so theta acts by the symmetry along the line, the horizontal line, and then we have a restricted root, which is of rank 1, and so we have an alpha. The alpha line downstairs corresponds to the variation cone, and we have gamma 1 dual, which is the only one, the only image of colors. Okay, and in fact, in rank 2 there is one more example with G2, but so I don't draw it because so the gamma I dual will be very near from the center, because you have to constrain by 3 or 6. So well, I didn't draw it, but so that you have to. So in general, so you will always have a picture with a strictly convex variation cone, and you will have some colors like this. So it will be always the picture that we will have. So there's no color inside the variation cone for this example. And in fact, the fact that there is colors, so you can separate colors and the variation cone says that G mod H is affine. So a symmetric space will be affine. Okay, so that's a property of symmetric. So now I want to speak about wonderful varieties. So that's why we are very interested in wonderful varieties. So definition. So I took my notes because I don't want to forget something. So X is wonderful if, so first, X is smooth. So it's complete. So it's wonderful of rank n. So it's a G variety. And there is an open orbit, G mod H. The complementary of the open orbit is a union of n divisor. So exactly the rank of the variety. And so di. And the di are smooth. So G stable, irreducible, and they intersect them by normal crossing. Okay, and the intersection of all di is non-empty. And last property is that if you take x prime in X, such that the set of I, such that x prime is in the I, x is in the I, is equals to the set of I, such that x prime is in the I. It implies that the orbit of X equals the orbit of x prime. So it means that the orbits of in X of G are entirely defined by the possible intersection of the divisor. So in particular, so maybe a corollary of the definition is that it's a simple variety in the sense that there is a unique closed orbit, which is the intersection of all the I. Okay, so so maybe I can give example. So if you look at toric, a wonderful variety, you will have only the point. Sorry? N is a rank, and there is n divisor, and it's the same, yes. Yeah. So toric and wonderful implies that X is a point, because it's complete, and you have only n divisor, so you can't have. So here you have n equals 2, and you have 3 divisors, so it's not possible. So if you want the variety to be complete, so there's no intersection between toric and wonderful. Another example is a wonderful completion of a symmetric space, which was constructed by De Concini and Procesi. Construct by De Concili and Procesi. So they describe how to construct it in all case. So it was so where am I? So which date? So it was in 83. So in 83, it was already not known that wonderful varieties are spherical. And in 96, Luna proved that wonderful varieties are spherical and projective. In fact, if we know that it's spherical, then by the hypothesis, so we have exactly n. So it must be complete. So it must cover the variation cone. So if we look at the colored cone associated, the colored cone must cover the variation cone, and there is exactly n divisor. So it means that there is exactly n edges in the cone, and also we have so we can also prove that we can't have any colors in one wonderful variety. So it implies that colored fans of a wonderful variety are like this. So you have the variation cone first must be strictly convex. And in fact, the cone is exactly the variation cone without color. So we have C equals mu, and we have no colors. So we can have colors, but we have no colors in the cone. The colored cone is C and empty set. So in particular, we see that it's unique. It is unique for each G mod H. When we fix G mod H, we only have one wonderful variety, and it corresponds to so the colored cone, which is the variation cone, and no colors. Okay. Okay, so now let me give what is known for the classification of wonderful varieties. Sorry? N is a dimension, no, it's a rank of n, it's not the dimension of n. Yeah, the dimension is bigger than the rank. It's always bigger than the rank for all spherical varieties. And it's equal only for toric varieties. So the rank and dimension is equal only for toric varieties. So in 2001, so for example, for all spherical varieties, so you have G mod H project in a G mod P, and the fibers are C star n. So here the dimension of G mod H is just the dimension of G mod P plus n. And n is the rank. Yes, I always call n the rank, and when I need to to give a letter for dimension, I will call it D. Okay, so a conjecture of Luna in 2001 is so he defines, so I don't want to give the definition of a spherical system. So the spherical system is more or less so the invariant I gave, so the weight lattice and the variation cone and all the colors, but with a lot of conditions. So I have 5 or 6 conditions on them, and then if we have a definition of spherical system, so it's the invariance with condition. The conjecture of Luna was a spherical system classified spherical wonderful varieties. Sorry? For wonderful varieties, yes. Yes. For wonderful varieties only. In fact, for all varieties where there is no color. So to add colors, in fact, it's the same thing that to contract some divisor of the variety. Okay, so we have a classification of wonderful variety, which was conjectured by Luna, by spherical system, which I will not give the definition because it's too long to give. And if you want to see this definition, I will put it in my notes in a simple case. So for strict, so I give the definition in my notes of strict wonderful, so strict spherical system, which corresponds to strict wonderful varieties, and so strict wonderful variety. So wonderful variety is strict if for all x in X, the stabilizer of X in G is the same as its normalizer. So it's a self-normalizing. Well, it's a very technical condition, but so strict wonderful variety implies that sigma is injective. So it means for each point, for each color or image of the color, there is only one color. So this is a definition in my notes for this particular part, and you will see that so it's very long and not very easy to read. But here I just want to give an overview of what is known and what is not known. So now let me say what is known. So the conjecture of Luna is true in the following case. So first, it's true for wonderful variety of rank 1, and this is the result of Acquiezer in 83, I think. So in fact, if in rank 1 we have all spherical varieties of rank 1, which contains 3 orbits, or we have non-all spherical of rank 1, and we only have two orbits varieties in that case. So it was also done in rank 2 and it's due to Wassermann. And it was done also before the conjecture of Luna, so it was done in 96, sorry. And then it's also known for G when the group is of type A, and it was done by Luna at the same time he gives the conjecture. And of type D, it was done by Paolo Bravi and Guido Pezzini. Bravi and Pezzini. In 2005. It was also done by Bravi in 2007, I think. Yes. And recently it was also done for strict wonderful varieties. Varieties were done by Bravi and Cupifutu. So it was last year, I think. And there's also another proof of Cupifutu of the same result after. So a shorter proof. The conjecture is this sign. So we have so the conjecture is there exists a classification of wonderful varieties. So we can classify invariants of the spherical varieties, the spherical homogeneous space corresponding to the wonderful variety, with some conditions. So yeah, so it's classified the wonderful varieties also. So if you classified the homogeneous space, then with the Luna-Wust theory, you also classified all Gmod H embedding or all wonderful Gmod H embedding, because for Gmod H, so if you have a wonderful variety, you have an open orbit, and for this open orbit, there exists only one, exactly one wonderful Gmod H embedding. So classify wonderful varieties or Gmod H. Sorry? So they are entirely classified. So in that case, it's totally classified by spherical system, which I don't tell the definition of spherical system. So it's so you have 5 or 6 conditions on the invariants of Gmod H. So the invariants of Gmod H are the weight lattice, the variation cone, the colors, the image of the colors, and also the stabilizer of each colors. And so this invariant satisfied condition in this situation, and so Luna remarked that so in type A we can classify all so you can classify all wonderful variety or wonderful so the wonderful variety or homogeneous space which admit completion, wonderful completion, the same. And so we remarked that it's classified, so some condition classified in type A, the all wonderful varieties. And then he conjectured that it's also the case for every type. And so it's only known for on type D and E. And it's also known for strict wonderful varieties for all, in that case, it's on all G of all type. And there's a recent paper of of Bravi and Luna about where they give a lot of examples in type F4. So it's an archive. I think it's from this year, so it's 2009. And maybe this is a good reference if you want to see exactly the conjecture, the definition of spherical. So this is a good reference. So to know all of these things. Okay, so in fact I was faster as I thought. So maybe if you have questions, ask me. And is there some question? Okay. So I will stop here. So it's 5 minutes. It's not so. So tomorrow I will do 2 talks. So one talks about Fano varieties. So I will talk about all spherical Fano varieties, and I will say how to generalize the results about Fano toric varieties to all spherical varieties. So the classification due to Batirev, and also results of Olivier Debar and Cynthia Casagrande. And on the second talk, I will speak about spherical varieties with Picard number 1. And so in the orospherical case, and also in the symmetric case. And I will give the list of all possible smooth, projective, and with Picard number 1 varieties. And so it will be more geometric tomorrow than this talk. Thank you.